Hi guys, in this video, we're going to continue on with OWL 4. So this is starting with number 9 in boiling points. The longer the hydrocarbon chain, so the longer the carbons and hydrogens you have, the idea of the gas state, or I should say the physical state, will increase to a solid. So if it's really small, it will be a gas. So usually carbons 1 through 4. If there are carbons 5 through 17, this is going to be considered a liquid, and anything over 17 would be considered a solid. So at C19, this guy is going to be a solid at room temperature. All right, next what we want to think about is the idea of boiling point. So the shorter the hydrocarbon chain, the lower the boiling point. So this guy would be the lowest, this guy would be the highest, and this guy would be the intermediate. And last question, again, thinking about what C5H12 would be at room temperature, this guy's going to be a liquid. Because again, it's about 5 carbons. 5 through 17 would be a liquid. All right, next we're going to think about solubility. And remember, like dissolves like. So if there's a polar compound, meaning that you have an oxygen present or a nitrogen present, they're going to be more soluble in water because of the fact that they are polar. So ethyl alcohol, because of that oxygen, is going to make this more soluble in water. Versus butane is just a bunch of hydrocarbons, carbons and hydrogens continuously. And they are nonpolar. Now this guy here asked which one would be the least soluble in water. Acetone, because of that C double bonded O, that carbonyl, that's going to allow it to be polar and therefore be soluble in water. Versus cyclohexane, again, just a bunch of hydrocarbons. They're not going to be soluble in water. And if we were to think about cyclopentane, which is going to be 5 carbons all together in a ring, and again, they're all single bonds, this guy is going to be, again, a bunch of hydrocarbons. It's going to be nonpolar. It's not going to be dissolvable in water. But also what's going to happen too is because it's going to have a relatively low density and it's going to be less dense than water, it's going to float. So this would not dissolve in water and then form a layer that floats. All right, now we're going to be moving on to the idea of alkenes. Alkenes are going to be these double bonds. So what's going to happen here is we're going to name the longest chain, just like we normally would, and we're going to make sure that we account for that double bond. So 1, 2, 3, 4, 5. To start off with, we're going to write pent because of 5, and because it's a double bond, we write ene. Now, the problem is we want to make sure that this double bond gets the lowest number present. So we're going to say that we're going to start over here and say this is the first carbon, this is the second carbon, because we want it to be on carbons 2 through 3. And so this would be 2-pentene. If we went the other way and said this is 1, 2, 3, it would end up being 3-pentene. And we want to stick with the smallest number possible. All right, submit our answer, and we're good to go. All right, here what we're going to see is that we're going to do a ball and stick figure here that's going on. What you're looking at is this is going to be where we name our longest chain. So 1, 2, 3, 4. Butene would be our longest chain. And again, it's butene because of the fact that it has a double bond. Now we have to account for that double bond, and it's going to be between carbons 2 and 3. So this is 2-butene. And then we have these methyl groups to talk about last. So because we have 2 methyl groups, we want to state that they're on carbon 2 and 3. But because there's 2 methyls, we write dimethyl. So this is 2,3-dimethyl because of those methyl groups, 2 for the double bond, and then but because there's 4, ene because it's a double bond. All right, and last but not least. So I can already tell just from looking at this, we're going to have to run this way to name our longest chain. All right, so this guy is going to be 5, so that's going to be pent. And again, because it's double bond, we write ene. It's located, that double bond is located between carbons 2 and 3, so this is 2-pentene. And then we have that methyl group to talk about. So this would be 3-methyl-2-butene. All right, I hope those make sense. All right, so now we have to deal with, oops, let me get rid of this guy here. Now we have to worry about what happens if there's more than one double bond. So if there's more than one double bond, we have to make sure to account for that. So we would have to say it's a triene or a diene or a tetraene. So let's go ahead and look at this guy here. 1, 2, 3, 4, 5, 6, 7. There are 7 in a row, so this is hept. And what we're going to have to make sure that we talk about is the fact that there's 2 double bonds. So this is heptadiene, to make sure that we mention that there are 2 double bonds. Now, we want to account for where those double bonds are. And again, we want to come out with the smallest numbers possible. So 1, 2, 3, 4, 5, 6, 7. We are going to put those double bonds on 2, 4. And so that way we have 2, 4 dash heptadiene. But now we also have to account for that methyl group. So this is 1, 2, 3, 4, 5, 6. So we're going to say 6, methyl dash 2,4 heptadiene. All right, let's try another one. All right, same thing here. We're going to name our longest chain. 1, 2, 3, 4, 5, 6. This is going to be hex, and then because there are 2 double bonds, diene. Now we have to state where those double bonds are, so we got to double check this and be careful. If we say 1, 2, 3, 4, it would be 2, 4, 4 hexadiene. But let's double check to make sure that that is the shortest numbers. I think it will be 1, 2, 3, 4. Okay, it doesn't really matter either way, so we're good with that. Now we have to add in our methyl group. 1, 2, 3. So this is 3-methyl dash 2,4 hexadiene. And last but not least, again, name our longest chain. 1, 2, 3, 4, 5, 6, 7. All right, we have hepta, and because we have more than one double bond, diene. Let's locate those double bonds. All right, so let's go ahead and figure out the order for these locations. So let's say 1, 2, 3, 4, 5, 6, 7. So it'd be on the 2nd and the 4th. So let's say 2, 4 dash. Now we have to take into account though that methyl group. So that would be the 6-methyl 2,4 heptadiene. All right, now what we're going to do is we're going to talk about reactions. So on these ideas of reactions, we are going to try to discuss how these reactions are going to take place. And what's happening here is we're creating something called halogenation, meaning that we're adding on halogens. Bromines are halogens. All they want us to do here is to name the alkene that reacted to form this compound here. So we're really only actually looking at the hydrocarbon portion. So kind of, if you will, omit the bromines for right now. And what happens here is when we see this guy, normally there would be a double bond. What happens is during this reaction, the double bond becomes broken and it becomes alkanes with these bromine. So what they're telling you is that there's a double bond right here. So pretend that this is a double bond instead of the bromines. And we're going to say, okay, let's look and see our longest chain. 1, 2, 3, 4, 5. So this would be pent. And again, because what we're not seeing is the fact that this would be ene. There's a double bond in between. The double bond is between the second and the third carbon. So we would say that this is 2-pentene. And now again, we have to take into account this methyl group. So 1, 2, 3, 4, 5. So this is going to be 4-methyl dash 2-pentene. All right. So this says draw the product that would form when 3-ethyl-2-pentene reacts with bromine. What we're going to do is we're basically breaking down that double bond. So what I suggest doing is actually drawing out your pentene group first, and then we can go from there. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this says 2-pentene, so it'd be right here. And then there would be an ethyl group on the third guy. Now what happens is we're going to break that double bond. And this is just going to become a single bond. Because what's happening here is we're going to put a bromine here, and we're going to put a bromine here. Now we can change these methyl groups to be something else. Oop. We don't want that. We want to make sure that we change it to not be these CH3s, but bromines instead. So we can go right here to this little guy, bromine, bromine, and we should be able to submit our answer. Okay, and now it says name the cycloalkene that would react with bromine to form the following. So again, where those bromines are, imagine that there's not the bromine and there's a double bond instead. So get rid of these guys here. Don't let that confuse you. We're going to name this guy as number 1, 2, 3, 4, 5, 6. So we have cyclohexene. Cyclo because it's in a ring, hex because there's 6, ene because there's a double bond. And the double bond we're going to put on a 1. But, this is where it becomes a little bit tricky. I would say that there's 1 cyclohexene. Sometimes I will omit the 1 because they would say, okay, if it doesn't state that there's a 1, it's just cyclohexene. But what we can do is talk about where the methyls are. And there would be 1 methyl because of where that methyl is. And then there would also be comma 4 because we have another one. This would be di because there's 2 methyls. And then we have our 1,4-dimethyl cyclohexene. All right, now we have another type of reaction that would take place. And what we're going to end up doing is we're going to break this double bond yet again. So what happens here is when they see this hydrogenation, we're adding hydrogens to it. So instead of it being alkene, we're going to go to an alkane. So what will happen is now imagine, if you will, there's no double bond. 1, 2, 3, 4, 5. So we have pent as our new product, but instead of it being pentene, it's pentane. Because again, we're going to break down that double bond. So now what's going to happen is we're going to switch this up. Instead of this being named as 4-methylpentane, because now again, we don't have a double bond anymore, we're going to go the opposite way. And this is going to be 1 2, 3, 4, 5. So this will be 2-methyl pentane. Okay, same thing here. We're going to talk about what happens when we form this new alkane via this hydrogenation reaction. So again, I would draw out your pentane or pentene. And again, we have it as 2-pentene and then 3-ethyl. Again, we're going to remove that double bond, and it's now going to look like this. And one final piece. It says when alkene 3-ethyl pentane, when catalytically reduced to 2,3-dibromo 3-ethyl pentane, draw the structural formula of the alkene. Okay, so it says an alkene forms 3-ethyl pentane when catalytically reduced and 2,3-dibromo 3-ethyl pentane when treated. Draw the structural formula of the alkene. Okay, so we want to start off with basically just making that 3-ethyl pentene instead. So let's go ahead and change this. Get our pentene really quickly. We know we have that 3-ethyl. And we're going to put this double bond here really quickly. Go ahead and submit our answer, and we're good to go. All right, the next reaction that we're going to see, again, we're going to break this double bond. And what's going to happen here is we are now going to be adding a hydrogen to one side of the double bond and the chloro to the other side. And so it's going to complete the reaction by drawing the major products. And what we're going to show is, again, that this double bond is going to be broken, and we're going to replace it with a hydrogen and a chlorine. Now, there is something that we're going to have to talk about for this really quickly before we get started, and there's something called the Markovnikov's rule. And when you're adding this HCl, the Markovnikov's rule states that you have to add across the double bond in a way that the hydrogen atom bonds to the carbon atom that has the greater hydrogen atoms already. So what's going to end up happening here when we break this bond, and so again, we'll draw out our little piece here. This one kind of looks like this coming up. Double bonded, like that. It's kind of what it looks like. What's going to happen when we break this double bond, the chlorine is going to go to this side here. And the hydrogen, which we don't have to show, will take the other side with the more or greater amount of hydrogens. So we'll submit our answer and we're good to go. All right, same thing here. We're going to try to keep idea of Markovnikov's rule. So we want to figure out what our alkene looked like originally, our cycloalkene. Again, we can see where that HCl is. So more than likely, it's going to be right here. All right. Get our cycloalkene on there. CH3. Double bond. Oh, let me get that. We don't want that. CH3. Looking like that. We want to get rid of this guy here because I didn't mean to put that in. And then have the CH3 come down just like that. CH3 come down like that. Submit our answer. We're good to go. All right, and then again, same idea here that we see that Markovnikov's rule. The side that has the most hydrogens will get the hydrogen to go with it. So we're going to see this guy here. We have that methyl group coming out. And we're going to add the chloro to this side here. Drop down, get our Cl. And we should be in business. Very good. All right, now for this reaction, again, we're going to break that alkene to try to make an alkane. But now what we want to do is we want to show what's going to happen with water. So now what's going to end up happening is we're going to end up making an alcohol. We're going to break down this double bond. And remember, when we think about water, we're going to think about it like this. So we're going to be adding on an OH group. And again, this is going to be thinking about Markovnikov's rule. And we're going to add the hydrogen to the side that has the most hydrogen atoms. So again, same kind of idea. We'll draw our little piece out. We got that double bond sticking out here. Again, imagine that that's here and coming down. We're going to break that double bond. Get rid of this guy because I didn't mean to put that on there. And now we're going to add our OH group here. Submit our answer, and we're good to go. All right, now this one wants us to show what the product would be, what would our, or I should say what our reactant would be as our cycloalkene. Again, you can see where that OH group was put. So there's gonna be a double bond here. All right, so now we're gonna do CH3, CH3, double bond. That CH3 is coming off. And we can submit our answer. And last one is actually the same as the one on the top. So maybe we'll get another one later on. Okay, for this one here, what's going to happen is it wants us to discuss the geometry behind it. So if we were to look, this is an alkane. There's no double bonds or triple bonds associated with it. And so it's going to ask us about this hybridization to take place of how many carbon atoms are present and how are they set up in this like sp2 or sp3 phase. And the way it's going to be set up is with this sp3 hybridized carbon atoms. So what's going to end up happening here, what they're going to show you is basically how it would be set up is that it's going to be this kind of like single bond tetrahedral structure. And that's where it gets this sp3 hybridized shape associated with it. Now this guy here is an alkene. So alkenes, when we go to look at them, let me show you the one before that, have it make a little bit more sense. It's going to have this trigonal planar shape to it. So it's going to be 120 degrees. So now we're going to see what the bonds are in between each atom. First guy, 120, because it's the double bond. Second guy, 120. Actually, I don't think, never mind, because that's trigonal planar. So that's 109.5 and 109.5. And the reason is because we're caring about whether it's the single bond or the double bond. The double bond will have 120 degrees. The single bonds will be that 109.5 because they're a tetrahedral structure. And if there was any triple bonds that we would see, we would end up seeing it as 180 degrees. All right, so this guy we're looking at in a 3D window. And we're going to see that we have a triple bond. So this is an alkyne. This molecule will have atoms in a straight line. And it has a triple bond associated with it because you're going to see that you have 4 right in a row. Again, we have a triple bond, and that would make it an alkyne. Now, speaking of alkynes, now we're going to care about alkyne nomenclature. So same way that we set it up before, find the longest chain, 1, 2, 3. Let me do this in a different color. 1, 2, 3, 4, 5, 6, 7, 8. Again, we're going to get oct, but instead of writing octane or octene, we're going to write ine. Now, again, we want to name where our location is for that double bond. And it, no matter what way we look at this, it's gonna end up on the 4th carbon. So we're gonna write 4-octine. All right, here we're gonna see the longest chain. So we're gonna say 1, 2, 3, 4. So this is gonna be bute. And then ine, because of that triple bond. It's on the 1st carbon, so we're not gonna say anything. We're gonna omit the 1. And then we're gonna say, okay, there's 2 methyl groups on the 3rd carbon. So we're gonna say 3, 3 dash dimethyl butane. And let me just make sure I'm going in the right direction. 1, 2, 3, 4. That would be correct. That's on the 3rd, so this will be 3,3-dimethyl butane. And they wanted us to add the 1. Okay, so like I said, sometimes OWL is very picky, and so sometimes it'll say to omit the 1, sometimes it won't. Here, it wanted us to show the 1. So this would be 3,3-dimethyl dash 1 dash butane. Gotta love OWL, but this is why I get to do it with you guys. You learn from my mistakes or OWL's very funny behavior. All right, so again, same thing here. We want to make sure that we can name the longest chain. I don't think it's going to matter either way what direction we go. So let's start this way. So 1, 2, 3, 4, 5, 6, 7. So then we'll have heptine, and it's going to fall on the 3rd carbon for that triple bond. Now we have to take into account those methyl groups. So this would be 2, 2 dash dimethyl because there are 2 dash 3 heptine. All right, so I hope these kind of make sense. Or at least you're getting there. All right, now what we're going to do is we're just going to name compounds with alcohols. And so what we're going to see is that we have these OH groups that are coming off of this hydrocarbon structure.